Okay, so this is the start of the next chapter on discrete random variables, and here's the idea. You have some sample space of a probability experiment, and you have an outcome, and you have an assignment of, of a number to that outcome. So you take the outcome and you get a real number. And that function is called a variable. In probability, it's called a random variable. If it's discrete, it has an associated experiment and sample space, and this is the definition of the random variable. So because the outcomes are random, the random variables are random. They have the same probability in line with the outcomes. Okay, so they're completely defined like this. If little s occurs, if say the probability little s occurs is say 0.8, and x of little s is say 50, then probability x is 50 is at least 0.8. It could be more if there are other outcomes that also are 50. So we'll see how this works. So the simplest and maybe the most important one, several of these have names, is the Bernoullis random variable. So for an example, so we'll say, and we'll usually write this with this similar sign, x is Bernoulli p. This means that x is either 0 or 1 with probability p as follows. This means the probability is equal to p, and the probability x is 0 is equal to 1 minus p. You notice I didn't refer to the underlying experiment here. You could think of many things like this. So for example, flip a coin and let S say equal the sample space heads or tails. And then we could set X of heads or tails equal to 1. So something like maybe I want to count heads as a 1, tails as a 0. Sometimes it's called success. We would say X of heads, the outcome heads, maybe is equal to 1. X of tails is equal to 0. Okay, how about another example? Say we roll 2 dice. We might consider all the sums, but we might just consider S to be equal to, S is all the sums in the way we usually think about it, but we could let S be, say, sum, the outcome sum is less than or equal to 3, or sum is greater than or equal to 4. Something like this. Okay, so we would set x of the first one be equal to 1, maybe x sum. Okay, we want to get a 2 or a 3. So then what would P be? So in this case, X is Bernoulli. Probability X is 1 is P. Probability X is 1 is here is 1 out of 36 plus 2 out of 36, so it would be 1/12. All right. Well, this is the idea. We can have, here, let's do another one. Example 2, we could have a sequence of Bernoullis. So sequence of Bernoulli P. Suppose we have this for an example. We flip 4 fair coins and let X equal number that are head. Okay. All right. Well, x could be then the range of x. Range of x is just 0, 1, 2, 3, 4. And I can think of x as the sum of 4 Bernoullis. So x is also, we could think of x equals x1 plus x2, x3 plus x4, where xi are Bernoulli 1/2 and independent. Okay, well then in that case, what do I have here? What is the map? Well, actually, if I think about these as all the outcomes, these can be as S. S is all the outcomes, right? So S could be, say, equal to let's say H1, H2, H3, H4. Maybe the second one is H1, H2, H3, H4 complement, etc. Until maybe I have all tails here. H2 complement, H3 complement, H4 complement, where HI is the outcome, or the outcome that I coin is heads. Okay, so S has all these outcomes, and I just want to map each one to the number of heads that are there. So this one gets mapped to 4. How many get mapped to 3? How many have 3 heads? Well, there would be 4, right? Because like this one has 3 heads, and then the complement could be at any spot. So we can see that probability x equals 0. Say all tails would be 1/16. There's only one. They're all equally likely. Probability x equals 1 is the same probability x equals 3. This, by the way, is same as probability all heads. And this would be 4/16 for each of these. And then the 2 is 4, choose 2, which is 6. You could also do that by taking the complement of these two, and then you see probability x equals 2 is equal to 6/16. Okay, in this case, this kind of random variable that is the sum of independent Bernoulli random variables is called a binomial. So x, we can define this, x is binomial, NP, if x is equal to x1 plus xn, and the xi are Bernoulli p and independent. Okay, and we can give the what's called the probability x is equal to one of its. I'll write this as a function in a second. Probability x equals k is just equal to the whether I have k out of the n are successes. So n choose k, and then I need the probability that I get a success raised to the k, probability I don't get a success raised to the n minus k. And this would be for k equal 0, 1, 2n. And otherwise it's 0, right? Otherwise it's 0. Okay, well, we can keep going. There are a lot more. We can keep going. Let's have another, just to give some more examples. So example, let x equals sum of 2 dice. And so the range of x is equal to 2, 3, up to 12. And you can compute those probabilities. You notice every time we want the probabilities x is equal to things. And this completely specifies the random variable. So let me just write this down. So we'll say the PMF, or the probability mass function of x is defined by P. You could write an x here, or it depends if it's already clear. P of x is equal to, this is a little x, probability big X equals little x. I could have called it K too. And it should be defined for every number, for every x in R, because it's just 0 if it's not possible. So you can make a real function out of that. So for Bernoulli, if x is Bernoulli P, what's the PMF? We'd have P of x, just define it piecewise, it's P or 1 minus P, and this is if little x is equal to 1, little x is equal to 0. What about a binomial P? We have P of x is equal to, sorry, I need two things here, right? I need binomial NP. I get n choose x, p to the x, 1 minus p to the n minus x, and 0. And this is if x is equal to 0, 1, dot, 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 to n, and this is else. I'm running out of time. Yeah. Okay, what about for the sum of two dice? And then, well, we have P of x is equal to, and you have this bunch of things it could be, 1 over 36. This is if x is 2 or 12. 2 out of 36, x is 3 or 11, dot, 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 right? And then the last one would be 6 out of 36, x is equal to 7. And then finally, you should probably, good idea, at least in your head, to think it's 0 else, right? If it's none of these, then it's 0. Okay, we have to stop, then we'll start the next one.